talked about the electromagnetic spectrum and the fact that our EM waves are how we transfer energy in the form of electromagnetic radiation. And light is only one type of electromagnetic radiation. And although we use light to see, and we've been creating light through burning fires and lamps for a very long time, our understanding of what light really is has kind of very evolved over a long period of time. Optics is the physics of light, and there are actually different branches of optics because of the different theories that kind of came about for how light behaves in our understanding of light based on experimentation. So geometric optics is going to be our focus for this course. And that is that light consists of rays that move in a straight line until it hits some sort of interface. It's been around for a really, really long time. It's attributed to ancient Greece and then developed more in Persia. Also have wave optics. This is the idea that light is actually a wave. That's kind of what we've been talking about with electromagnetic waves, which was developed by Christian Huygens in 1690. That adds more concepts such as interference of waves, and eventually Maxwell was like, hey, we have electromagnetic waves and light is just one type. We also have quantum optics or modern optics, and the idea that light is a photon and it actually behaves like a particle. So sometimes you hear about the wave-particle duality. And Max Planck and Einstein were the ones that were kind of the pioneers of modern quantum mechanics and optics and so forth. So when we talk about visible light, okay, the light that is generally seen by our eyes, most human beings can see wavelengths from 700 nanometers right here on the red to violet, Roy G. Biv, the violet is over on the right, at approximately 400 nanometers. Okay? Each individual's eyes kind of varies a little bit, but that is the general range of human eyesight. Other animals can see into the infrared or into UV. And although you're not required to memorize the values for the entire spectrum, I do suggest you have a basic understanding of the general ranges of visible light in terms of the color spectrum. For example, red at 700 nanometers, violet at 400 nanometers, and kind of our yellow-green comes in here around the middle, kind of in between that. So have kind of in the back of your head, because there might be a question that asks, hey, here is an example wavelength. What color would you expect it to be? Now, I mean, if it's, you know, something right here and one person says blue and one person says green, okay, it's obviously not red. It's obviously not purple. You'll be okay. Okay, so I'm not going to grill you down on that. Just have kind of a general idea of where these ranges are. So we're going to focus on geometric optics, which is that our light consists of rays. A ray is an infinitely thin beam of light that we represent with an arrow, a straight line arrow. In a vacuum or a single uniform medium, we assume that that arrow is a perfectly straight line, and it will stay a straight line until it encounters some sort of boundary in which the medium changes. If your medium is not uniform, then you will get a ray that will bend. So for example, you might see a straight ray that comes here into the surface, and then it might bend away or towards, it might get reflected. But as long as we're going from one uniform medium to another, that ray basically just changes directions. In real materials, we cannot keep density constant, so light travels much more interesting patterns through materials. Now, we can only see objects because light has bounced off of those objects. So the rays in geometric optics that reach our eyes are what we see. So if I see a yellow pencil, that pencil is yellow because yellow light has been bounced off of that pencil and has reached my eye. If I see black, I'm actually not seeing the object. An object that I see as black is because I'm actually not seeing the object at all. Because black absorbs all of the visible wavelengths of radiation. So when I'm seeing a black t-shirt, I'm actually not seeing the t-shirt at all. It's kind of crazy. Whereas white light, when white light reaches our eyes, we're actually getting the entire spectrum of color reaching our eye. So in terms of that reflection, light can be reflected, transmitted, or absorbed. So reflected means bounced off, transmitted means passed through, and then absorbed means it hits the material and is neither reflected or transmitted. So if our reflected rays end up reflecting in nice uniform geometric patterns so that their angles stays the same before and after, that's called specular reflection. Like spectacles, mirror-like for that. That's what specular means. Okay, that's specular for that. Real surfaces produce diffuse reflection, so we generally don't get very nice images on rough surfaces. When you can look at a lake or a pond or a pool and you can get that perfect mirror image of the trees. So if we've got like some sort of pond right here and we've got like a tree, when I can see that tree in the water, that's because the water is being very smooth. But if there are a bunch of waves in the water, I cannot even sometimes see the tree at all, even though light rays might be leaving the tree and hitting the water. That is our diffuse reflection. So when light hits your clothing, you don't see reflected images in your clothing because the light that is reflected is being transmitted by each of the different fibers in a different direction. And so we are not getting images off of that. So we're going to focus on specular reflection. And for specular reflection, our assumption is that the reflected light leaves the surface at the same angle it was incident. Incident means coming in towards. So this is our original ray. When you see incident, think original. So our incident ray is going to be the arrow over on the left. And our angle here, that is our theta I, theta incident. And then our theta R, that's our reflected. And be careful, R is going to be used interchangeably for reflected and refracted. So you have to be aware when you're dealing with a situation that is reflection and a situation that is refraction. And a refraction we'll see is bending. So in this case, that is our reflected. So this is incident. And this is reflected. So we have the law of reflection, which basically says theta I must equal theta R. As long as your angles are measured from this line right here, which is the normal. So remember, normal in physics means perpendicular, like the normal force. So the normal is perpendicular to the surface. Now, in terms of the law of reflection, and that's what this is sometimes called, the law of reflection, but it should be the law of specular reflection. The most complicated problems you might see with this might be something where you have like some weird wonky surfaces of mirrors and say that each of these is a mirror. And they might give you like some sort of incoming ray of light, and then it reflects, Well, I guess it wouldn't hit that one, but you know, they may give you some like initial angle here, and they might want to know like what angle does it leave the surface or something. In which case you would have to kind of break it up into smaller pieces. So I would draw like a normal here, and I'm like, okay, well this angle right here, I'm going to call it theta 1, is going to be 90 minus like what I'm calling theta I here, whatever they gave me, or theta 0. And then this right here, I'll call that one theta 2. Well, theta 2 would have to equal theta 1 because of my law of reflection. And then you could kind of go around. I'm like, okay, well, if this is a 90-degree angle, well, then that angle right there is going to be 90 minus theta 2. And then I'm like, okay, well, that's a 90-degree angle. Then this angle right there is going to be like 180 minus theta 2. And then I've got a normal here. And basically you keep going kind of with the geometry to figure out, okay, well, what eventually is it when it's over here? Okay, that's basically as complicated as the law of reflection gets. Now, we will look at curved mirrors in the next lesson, and that gets a little bit more interesting and fun because you're going to have different rays of light that intersect different parts of the curve. And if I have a ray of light that hits here, you know, it might bounce this way. It's still going to follow the law of reflection. That is to say, take the tangent of the curve at whatever that point of reflection was. I could draw the normal, and then I still get that theta I here would equal theta R. So it's true even for a curved mirror, but the problem is if I get a different ray that intersects a different part, the angles at which they intersect are going to be different. So even though we are going to follow the law of reflection, you're going to get very, very different angles depending on which rays that you are looking at. But it still holds. Now, with refraction results in a change in direction due to interaction with a medium. So if you picture like when you have like a cup of water, and you might have seen like the broken pencil kind of idea, and that the pencil appears like it's broken when you look at the air compared to the water, or like with a straw. That's happening because your light is going to travel at different speeds in different media. So our speed of light is only the speed of light in a vacuum. If we're not in a vacuum, then what's going to end up happening is the wave speed is going to change, and that's going to cause the light to bend. So like in this image right here, you're looking basically at bubbles, and so the background of this image is being distorted because of the change in speed of the wave as it moves from air into the bubble and then back into air. So our speed of light in a vacuum is going to be 3 times 10 to the 8th meters per second, but you have to be careful. We will use speed of light in a vacuum usually for air because it's really, really close to being a vacuum, but it's different in water and any other material. So in the medium that you choose, you're going to have a different wave speed V. I will sometimes use more of a curved V for the wave speed. That's actually, some textbooks use the Greek letter nu. That's a lowercase nu for wave speed. So you might see me curve that V. That's also because sometimes I don't want to confuse it with like V for volts, or there's so many V's, like volume, and so forth. But C is our speed of light. And what's going to happen is you can see that the ratio here, that this is our max value. We can never have a speed that is going to be faster than our speed of light. So what happens is our wave speed is going to be slower than in the vacuum. And if you think about it, it's based on inertia. Because if my light is having to pass through even air, there's a whole bunch of molecules and so forth that are getting between the incident light and its destination. And so that is going to slow down the wave, just like when you do like sound and so forth. The denser the material, the slower the wave travels. So our index of refraction is going to be a variable that we're giving lowercase n. And it represents basically kind of that density of the material. It's not actually the density of the material, but it is the ratio of the speed of light in a vacuum to the speed that the wave is actually traveling. So this is a value that we find empirically. That means through experimentation. So we do a whole bunch of experiments and figure out, okay, for water, this is what the value is. For mercury, this is what the value is. Okay, so you get different values of the index of refraction for different densities. Now, technically, remember that things like density changes with temperature. So air can have different indices of refraction. And if you've ever seen a mirage, or we're kind of like, you've got like the hot pavement and the cooler air, it's not even that cool, but it's just a little bit cooler, you might sometimes see kind of waves coming off. Those waves are ripples in the movement of the light due to the different densities of the air, and that's how you get kind of that mirage effect. And our eyes, especially when you're having a heat stroke and stuff like that, can play tricks on your brain based on what those mirages are doing. So our wave speed is wavelength times frequency. So when you are looking at that equation, we have n is equal to c over our wavelength times frequency. So what ends up happening, and this is something you need to memorize, is that when your waves travel from one medium to another, so like when you're going from the water to the air boundary, what ends up happening is your frequency stays the same. Your frequency stays the same. You have to memorize that. So for example, if we solve this equation right here for wave speed, we get that wave speed is going to be c over n, but we also know that our wave speed is wavelength times frequency. So what that tells us is that our frequency is constant. The speed of light is actually a constant. So what ends up happening is that if our index of refraction goes up because we go into a denser medium, then that means that our wavelength has to go down, and so our wave is not going to travel as far as it would if it was in a vacuum. So you could summarize that by having our wavelength n in some medium n is going to be the wavelength over n. So this would be like the wavelength in a vacuum over n for that material. So it's the wavelength that changes, which is why the wave slows down. Okay, the wave slows down because the frequency stays the same, but your wavelength gets smaller. So as long as we are not traveling near the relativistic limit, okay, our index of refraction can never be greater than 1. It's close enough for our purposes. For water, the index of refraction is 1.33. For glass, it's about 1.5. You are not going to be required to memorize these values, okay? They would be provided for you. So if we wanted to say calculate the speed of light in a diamond has an index of refraction of 2.42. We know that by definition, our index of refraction is c over v. So if I wanted to find the new speed of light in that diamond, I would have to do c over n, which is going to be 3 times 10 to the 8th meters per second over 2.42. So if we plug that into a calculator, we get that our wave speed in the diamond is going to be 1.24 times 10 to the 8th meters per second. So our wave has slowed down as it enters diamond. So Snell's law is a numerical method for calculating how much a ray bends as it enters a new material. So what we're going to do is we're going to have theta A be the angle of incidence and theta B be the angle of refraction. Now we're using A and B instead of I and R because it doesn't actually matter which one is the incident and which one is the refracted if in the equation, because it's really just based on ratios. So for example, when you have a light ray from air and it hits this boundary between air and water, what ends up happening is we measure our incident ray, of course, from the normal, because we always measure our angles from the normal. Our light ray, as it travels through water, is bent, okay? When you look at the incident ray, it would keep on traveling at like that angle. So what has happened is my ray has bent. We call that bending towards the normal. You're going to hear that terminology, has bent towards the normal. And so our refracted angle is still measured from the normal, and we can see that in this case, theta A was larger than theta B. And in this case, the index of refraction of water is about 1.33. With air, it's approximately 1, okay, because it's very close to being a vacuum. So our refracted angle ends up being smaller than the incident angle. If you were to start with that flashlight in the water, then our theta A would say be here. Trace out where that incident ray was going, I can see that the refracted ray has bent away from normal. So I have bent away from the normal. So this bending towards or away from normal can mathematically be calculated using Snell's law, which is this guy right here at the bottom. So it's based only on the indices of refraction and whatever the initial angle is. So you can see that it doesn't really matter which one is incident and which one's refracted because both sides of this equation are basically the same thing. So we can tell, because our air had a smaller index of refraction than our water. Anytime you have a ray go from a lower N to a higher N, your ray is always going to bend towards the normal. If you start in a high N material and go into a low N material, you are always going to bend away from the normal. And mathematically, you could prove that using Snell's law. So like in this first example, we have light passing from air, which we assume has an index of refraction of approximately 1 because it's very close to being a vacuum, into water with 1.33 for our index of refraction. So if you were to look at Snell's law and plug in 1 over here on the left for air, because that was our incident, and here we have water, I get sine of theta A is equal to 1.33 times sine of theta B. In order for that to be true, theta A has to be larger than theta B, which means I had to have a smaller angle than I started with, and so therefore I have to bend towards the normal, which is that vertical line. So there you go. Bending towards the normal, because it's going to slow down in water. It's not going to be able to travel as fast. A is less than theta B. Because of that difference in density, our light has to bend away from the normal because our angle has to get bigger as it moves through that transition, because it's moving from a slower speed to a faster speed. So as I mentioned, it doesn't really matter which one you choose as A and B as long as you know one side is incident and one side is reflected. I always use subscripts when working problems like this. Instead of using like A and B, if I'm doing air and water, what I would probably do is I would say NA sine theta A is equal to NW sine of theta W. I will use subscripts that represent the material because I am less likely to plug in the wrong value into the equation if I'm using good subscripts. But that's me. It's up to you what you choose to be your subscripts in this case. Unless it's a non-numeric problem and it defines it for you and then you have to use their variables. And of course, you have to remember that theta is always the angle that the ray makes with the normal. They won't always give it to you. Like I said, they could give you this and call that theta I or theta 1. But that is not your incident value because your values must be measured, your angles must be measured from that normal. Snell's law on its own is really not complicated. Just make sure that you're using degree mode for your calculator. What's more interesting are things like prisms. So the first thing I do when I'm working a problem like this is I trace out what's going on. Okay, so I think about what all the steps are. I kind of draw my ray diagram to kind of figure out what's bending towards or away to get kind of a conceptual understanding of what's going on. So sometimes the normal will be drawn for you, but if the normal isn't drawn, you need to make sure you draw the normal in and make sure that whatever initial angle they give you, which in this case is 23 degrees, is normal to that surface. So that I'm starting in water and going into glass. So I'm going from a low N into a high N. So if I remember from before with Snell's law, that's kind of like when I started with air and went into water. So I'm going into a more dense medium. So that means I'm going to bend that light towards the normal. So to do that, I start by drawing a projection of what it would look like if the ray was just transmitted through. So in that case, that's going to go just kind of like that. And then I'm going to draw that I bent towards the normal. So I need to go towards the normal. So I'm going to say pick that right there. And I'm going to assume that that goes all the way and strikes the other surface in a straight line. I know I didn't necessarily draw a straight line. And then that angle right there I'm going to call theta 2. That's my second angle. So I'm going to assume that that glass was uniform density, so that purple ray is going to travel straight until it intersects the glass water barrier. And then I'm going to draw another normal. So there's another normal here with the surface. And what's going to happen is that in this case, I'm going from glass into water, so that's going from high N to a lower N. So I need to bend away from the normal. So that light ray is gonna then have to, if it had continued, it would have continued like that. But I have to bend away from the normal. So there's my normal, so I need to go away from the normal. And then I'm going to call this one theta R because that's going to be my kind of my final answer. So this is not a one-step problem because I have several refractions and I also have a weird kind of angle thing going on right here because this angle right here, I'm going to call, let's see this guy right here. I'm going to call that one theta 3. That's the incident angle for the second refraction is not theta 2. I mean, there might possibly be an angle at which they are actually the same, but I cannot assume that they're the same. So I'm going to need to find a way to figure out what that angle is. So we're going to have to do a little bit of geometry. So I have to start looking for things that I know. Now, you may not remember things like law of sines or cosines or all sorts of things that I don't remember. So you use whatever resources make sense to you, but you have to make sure you communicate those to me on a test. What I would do is I rely a lot on other simpler triangles. So, for example, between this line here and my surface here, there's a 90-degree angle. So I know that this angle right here, which I'm going to call, I don't know, theta 5, or just, I don't know, yeah, I'll call this one phi, just phi. Phi is going to be 90 minus theta 2. And then, if I look, I have a triangle that is here. It's not a right triangle, but this angle right there, which I'm going to call phi 2, is the third angle in that has to add up to 180. So it's going to be 180 minus 45 minus phi. So that's going to be 180 minus 45. Phi is 90 minus theta 2. So if I simplify that down, I get phi 2 is going to be 45 minus theta 2. So I'm going to be able to make use of that. The reason I wanted to find that one is because if I look here, there's another right triangle. And with that right triangle, I can see that theta 3 is going to be 90 minus phi 2. So I'm using kind of these triangles that I can find to create relationships between my variables. So I'm going to write those there because I'm going to need those here in a little bit. So then what I can see is when I start combining those together, if I plug in for phi 2 right here, I get that theta 3 is going to be 90 minus 45 minus theta 2. So this tells me that theta 3 is going to be 45 minus theta 2. There might have been some easier way to do that. If you found an easier way, more power to you. Okay, sometimes when we're working problems like this, you just have to go with the flow and figure out what triangles you can find. So I'm going to write that down over here because I'm going to need that later. So theta 3 is 45 minus theta 2. Oh, and what's kind of fun is I actually think I just saw an easier way to do that. So if I look over here, that's probably a lot easier. So since this is a 45, 90 triangle, I've got a 45 degree right there. And then this angle right there must also be 45 degrees because that's supposed to be horizontal. And then I've got a 90 degree right there. So if I was looking just at this big triangle right here, I can see that theta 2 has to equal, no, not equal, but theta 2 plus 45 plus 90 plus theta 3 has to be 180 degrees. So I get theta 2 plus theta 3 has to equal 180 minus 90 minus 45 is 45. So that also tells me that theta 3 is 45 minus theta 2. Different triangle that might be easier. That was not what I saw the first time, but now you can see that there are different ways to come up with that answer. Okay, so now that I've kind of traced out my ray diagrams, made some sense of some of the geometry and the trigonometry, now I can start solving for the angles. So the first thing I'm going to do is I'm going to solve for going from water into glass. And I'm going to use Snell's law. So I'm going to say that n water times sine of theta water must equal n glass sine of theta glass. Now I want to relate this to the variables that I have already established. So what I can see based on the variables I've established, I'm going to define theta w as being my theta I, which is 23 degrees. NW is going to be my 1.33. On the other side, theta glass is what I'm looking for, and I've defined that as theta 2 in my equations. And then N glass is going to be 1.50. So I'm looking for theta glass. So I'm going to algebraically solve before subbing in any numbers. So I'm going to get that NW times sine of theta W over N glass is going to equal sine of theta glass. Now, I don't necessarily need you to show all the algebra, but we're not necessarily all on the same page with math. So then to undo the sine, I have to do sine to the minus 1 on both sides. So that gives me that theta glass is going to be sine to the minus 1 of NW sine of theta W over NG. And then I show my numerical substitution. So theta glass is going to be sine to the minus 1 of 1.33 times sine of 23 degrees over 1.50, which when you plug in gives me an angle of about 20.2 degrees. So I said that I should bend towards the normal, which means I should get a smaller angle, and I did get a smaller angle. So that tells me that theta 2 is going to be 20.2 degrees. So then when I look just kind of at my transitions, I need to find theta 3. Theta 3 is 45 minus theta 2. So theta 3 is going to be 45 minus 20.2 degrees, which gives me theta 3 is equal to 24.8 degrees. Please always show your substitutions. So theta 3 is 24.8 degrees. So the next part is I need to go from glass back into the water. So I can see that I'm going to set up Snell's law again. So I'm going to get N glass sine theta glass is equal to N water sine of theta water, but these are not the same angles I had before. So in this case, my theta for the glass is theta 3. So I'm going to write N glass sine of theta 3 is equal to NW, and I defined my outgoing angle as theta R, so sine of theta R. So solving algebraically, I'm not going to go through all of the steps this time, but I'm going to get theta R is going to equal sine to the minus 1 of NG sine of theta 3 over NW. If you want to see that algebra again, go back to the other earlier part. Plugging in, I still show all of my substitutions. Is going to be sine of minus 1 of N glass is going to be 1.50 times sine of theta 3. Theta 3 we said was 24.8 degrees over N water is 1.33. And that gives me that theta R is equal to about 28.2 degrees. There might be some rounding differences depending on the number of steps that you showed. So with this, I can see that I get an outgoing theta R that was bigger than my incoming of 24.8. Let's take a look at some visuals. So I've done this as a lab sometimes when we have a little more time. And so what we can do is we can actually say, kind of experimentally, kind of just play around with what happens with your different materials. So in this case, I'm going from air into water. And so you can see that compared to the ray that was actually traveling through, that my ray has bent towards the normal. There's also a reflected ray, so only part of the ray actually gets refracted. Some of it gets reflected with the surface initially. And I can actually see that the darkness of that ray is actually changing. So the shallower my angle, the more that gets reflected than refracted. I can actually change my indices of refraction. So instead of starting in air, I could start in water, and then I can go into air. And you notice something weird actually just happened with what I was there. So right there, there's actually no refraction whatsoever. And I can see that as I play around with this, there is an angle at which that refraction completely disappears and it becomes all reflection. The angle at which that occurs, at which we go from having some refraction and reflection to having just reflection, is called the critical angle. And that's what we are going to take a look at next. So if we follow from that little simulation, we start here with Snell's law. What ends up happening is you can rearrange and find that sine of theta 1 is basically the ratio of the index of refractions to sine of theta 2. If n2 is very, very, very small, or at least, not doesn't have to be very, very small, but smaller than n1, the largest possible value of sine of theta 2 is going to be 1. And that's going to occur when theta 2 exactly equals 90 degrees. That's when you're going to get the largest value of sine of theta 1. So we define that critical angle because after that, if you go any larger than that angle, that is when you get total internal reflection, because Snell's law can no longer be satisfied. And this is only possible when going in from a more dense to a less dense material. When we started that simulation, we started in air and went into water, and I could move that angle all around. And although I got more and more reflection, the steeper that angle I got, there was never a point where the refraction completely disappeared. But when I switched and I started in the water and went into air, that was when I could have that critical angle and have total internal reflection. We call it totally internal reflection because it's reflected back in towards the original medium. So that critical angle is a value that we often are asked to find in problems. So what you do is you define that your sine of theta 1 max is equal to sine of theta crit, and that's going to be n2 over n1, and that's because you're defining sine of theta 2 to equal 1, because you're doing sine of 90 degrees for this term, which is equal to 1. So we're then defining theta 1 max to be our theta critical. Okay, so that's what we are doing in this case. So when we have absolutely no refracted light ray, we call that total reflection or total internal reflection. And theta C is our critical angle, the angle at which that occurs. And our big assumption to solve that problem is it occurs when theta 2 is 90 degrees. And it only occurs when you're going from a more dense into a less dense medium. So we can see this again. So what happens is you have, initially you have some reflected ray, and that would follow the law of reflection, and then you have some that is refracted. As you get closer to the critical angle, you can see that you get more reflection and you get less refraction. Isn't it annoying that reflection and refraction sound so similar? When you are at greater than the critical angle, what ends up happening is there's absolutely no refraction. And you get all reflection. They didn't show it here, but when you are at theta C, what ends up happening is your theta R is equal to 90 degrees. So you still won't see any refraction because the refraction is traveling along the surface. Kind of looking at this again, we have light ray, we have like the angle is straight vertical through those surfaces, so if our incident light is normal, then what happens is you get basically transmission and reflection. So the yellow ray is transmitted through, and you get pure reflection kind of coming back. And then as you start to increase the angle, you start to get some reflection and some refraction. You increase it more, and you keep increasing it until you're at that critical angle, and then that's showing that refracted ray is going along the surface of the boundary layer. And then beyond that, you get the total internal reflection. A real-world application of this is fiber optics. So if you've ever played around with fiber optics, you might have seen these like at amusement parks or like on the 4th of July or something like that. What ends up happening is these are little fibers, and at the bottom of this little device there is a light. And that light enters the fiber optic cable and then is totally internally reflected because you're going from a more dense, a higher index of refraction medium into air, and that causes total internal reflection. And so then that light gets reflected, completely reflected. So if I had my eyeball here, I would not see anything. I would not see any light coming out. No light coming out. I would just see the plastic. But if I was to stick my eye here, I would be able to see the light coming out. And that's what you're seeing here is you see little pinpricks of light on the very top of those, but you don't see any light coming out of the sides. This actually can occur naturally without having to create fancy materials. There is a mineral called ulexite, which is actually a boron-based mineral. And if you were to look at it, it's actually made of very thin vertical fibers. Those little crystals grow vertically naturally. And they act like little fibers. So you can see, it's kind of hard to see here on this image, but this is actually a projection onto the top. If you were to look at that mineral from the side, you would not be able to see the words, and it actually kind of looks like it's a TV screen because it's transmitting that light up to the very surface of the mineral. If we were doing this in person, I actually have a sample of ulexite back when I was studying optical mineralogy in college. I thought this was one of the coolest things I ever saw, so I made sure to get a piece of ulexite for myself. It is very, very neat to see that projection, and that is due to total internal reflection. This is also how fiber optic cables work. Because you are the information travels near the speed of light. You get very, very fast transmission through the fiber optics for your internet. All right, so while finding the critical angle on its own is not super tricky, it's just an application of Snell's law. They like to toss in kind of some more interesting types of problems. So we're going to look at this one. We want to find the incident angle theta I for which light strikes the inner surface of a fiber optic cable at the critical angle. So what we're going to do is we are going to assume that our light is incident at an angle of theta I. So I'm going to draw that so that horizontal line is our normal coming out of the surface of that fiber. Then there is going to be refraction at that first surface. Now that refraction is not our total internal reflection, because our reflection only occurs, our total internal reflection only occurs when you go from a more dense medium to a less dense medium. So the air to fiber optic is not going to be what gives you the total internal reflection. It's going to be this second part once the light rays starting in the fiber optic and trying to go back out into air, it can't. And instead it gets reflected back in on itself. So that is what we're looking for. So the light is going to have an initial refraction. So we're going to call this one theta F. That's going from air into the fiber optic material. So using Snell's law, we have that our Ni sine theta I is going to be Nf sine theta F. Because we're starting in air, Ni is just 1, so that's where Ni disappeared to, is because it is just equal to 1. So now the light is going to strike the fiber at an angle here. That is going to be 90 minus theta F. Because our theta F is going to be that angle right there, because this line is parallel to that line. And then we've got our 90-degree angles here. So this angle right here, that is actually our incident angle for the second part, is 90 minus theta F, which is shown right there. So that angle, which is our incident angle for the second part, is 90 minus theta F. And then when we are at the critical angle, we are assuming that our refracted ray at that fiber air boundary is now 90 degrees. So, and this 90 degrees minus theta F is our critical angle. So on our incident side, we have NF sine of 90 minus theta F, which is the same thing as theta C, is going to be NF sine of theta C. And then using Snell's law on this side, we have NF sine of theta C is going to be NA sine of 90. But that NA is our air. So that's equal to 1. Sine of 90 is 1. And that sine of 90, once again, that is for our assumption that we are at the critical angle and that ray is getting refracted at 90 degrees. So then you end up with solving for our theta C right here. Sine of theta C is going to be 1 over NF. Okay, so dividing the NF to the other side. And then all you have to do is you need to solve that. And then we use that sine of theta I is equal to NF sine of theta F to go back here to the first part to go through and solve. So if we were to do this with numbers, let's say that our NF is going to be 1.4. And we want to know what theta I will give us that critical angle. So we start with the end, okay, over here. Remember, this is our theta critical. This is N for air. This is N for our fiber. So this side on the right all just ends up equaling 1. So then you divide the 1.4 over to the other side. So we get sine of 90 minus theta f is 1 over 1.4. So we need to undo that by taking sine to the minus 1 on both sides. So when you do that, we get 90 minus theta f is 45.58 degrees. So that gives us that theta f is 44.41 degrees. Now, that is not the answer to the problem because we're actually looking for this theta I back over here. So the next thing we need to do is we need to solve this part. We've just found theta f. So then we do that air into fiber start. So this is going to be N air sine of theta I is equal to N of our fiber sine of theta f. So, and that tells us that sine of theta I is 0.980. So taking sine to the minus 1 on both sides, we get theta I is 78.5 degrees. This is a very, very, very large value. So if you want to be able to come in more straight on, which is much improved, then you actually have to do some thin layer. You add another layer, add a different coating, and this gives us some thin film reflection. And we're not going to do thin film stuff, but that's a completely different process. And that thin film allows you to be able to have your incoming ray come more normal. So just some other examples of total internal reflection. A periscope. If you picture like a submarine movie, you've got like water down here. And you've got, a captain of a ship down here kind of looking into that periscope. That's very, very not to scale. But if he's looking at that periscope, the reason it works is because if you're trying to find like a boat or something like up here, what happens is the light from that boat comes in and reflects off. Total internal reflection comes down here, does total internal reflection, and then comes into the eye of the captain down there. Okay, so that's how a periscope works. Also, diamonds are all nice and sparkly and colorful because of some of this, a combination of total internal reflection and also some dispersion from the separating of the colors of light as they enter different mediums. And so that's just the very last topic. We're not going to do a ton of calculations or any calculations with this whatsoever, and that's just dispersion. So we've actually been treating everything as if we had a single value for the wavelength of light. So we could have done red light, we could have done blue light, and that would work. But technically, every wavelength has a slightly different speed of light in the material. So what ends up happening is that the index of refraction is actually dependent on the wavelength of light. So if I have blue light come in to the prism, it's going to have a different angle of refraction than red light. It's going to bend more than the red is. So you're going to get a separation of colors. And this is actually how you end up getting a rainbow. Because your red wavelengths are longer, they are going to be less affected by the transition from the boundary. Your shorter wavelengths, like the blue light, are going to be more affected. So your blue light is going to bend more than your red light. And the reason of that is by the properties of the material. And how much dispersion, how much separation of colors you get is dependent on the material. So, for example, if I wanted to make a prism so that I could see the rainbow of colors. You might have done this. I want to pick something like this, like silicate flint glass. And that's because there is a big difference between the index of refraction of the violet light and the index of refraction of the purple light. It's not huge. It's really not that big of a difference. It's still within 0.1. But compared to some of the other types, like quartz, that's sand, silica, okay, that's your quartz, has much less of a difference. So you're going to not get quite as big of a rainbow with quartz as you would with a silicate flint glass.